Yeah, maybe it's time for open
recording in
seminar.
progress.
So ladies and gentlemen, good afternoon. So welcome you to participate in this open seminar in Frontier of Nuclear Physics. I am Hiyama from Fudan University. Today, we are very happy to Professor Emiko Hiyama to present a seminar. Professor Hiyama is from the Tohoku University, so she is one of very active scientists in nuclear theories, especially for the field body physics and hypernuclear physics, as well as hadron physics. So this seminar series is hosted by Fudan University, as well as Shanghai Research Center for Theoretical Nuclear Physics, National Science Foundation of China. The seminar is also co-organized by the Journal of the Nuclear Science and Techniques, as well as its Chinese edition, Nuclear Techniques. The seminar is open to the public, particularly for the nuclear physics community. This seminar is also live shown by the CoShow.com. Professor Hiyama will give a talk structure of the heavy hadron nuclear, hydrogen 7 with the triton plus 4 neutron cluster model. Before the talk, so I would like to make a brief introduction to Professor Hiyama. Professor Emiko Hiyama is the director of the Strangeness Nuclear Physics Laboratory at the RIKEN Nishina Center and a professor at Tohoku University. She received her PhD at Kyushu University in 1998 after being a researcher for KEK and an associate professor at Nara Women's University. She moved to RIKEN in 2008 and became laboratory director in 2018. Her main research field is theoretical nuclear physics, in particular, applying accurate field body problem calculation method to hypernuclear physics, unstable nuclear physics, and hadron physics. She has published more than 200 articles and review papers, and was awarded in Saluhashi Plaza in 2013 for developing computational methods for precise solution of the quantum n-body problem. Currently, she is also served as the editor of the Physical Review C and European Physics Journal A. So she is quite active, famous in our nuclear physics community. So let's welcome her talk. So, Hiyama-san, please.
Thank you very much for the kind introduction. And then I'm very happy to give a talk here and about my recent work about hydrogen 7. Okay, and these are my collaborator from Strasbourg and Limantas Razaskas and German Carbone from Sacre. And then just actually, last year, last May, this my paper already published in this in physics release. So therefore, if you're interested to end my result about hydrogen 7 in detail, please read my paper in this physics release B. And then just about before the hydrogen 7, I briefly introduce about tetraneutron state. And this is my outline of my seminar. And after introduction, and as mentioned before, that I give a talk about tetraneutron state, tetraneutron system, and also after that, I discuss about hydrogen 5 together with hydrogen 7. You can see that especially in tetraneutron state is also the surrounding and around this triton and core. So therefore, in terms of that this tetraneutron, in terms of tetraneutron system, and so I think that this hydrogen 7 might be useful system. Okay, so let's begin. Okay, so the first I shall talk about why I studied about hydrogen 7. Okay, and you can see that and the tetraneutron system has been observed by RIKEN and in 2016. And then this is so the if this observation is reliable, and we observe the no isotope nucleus. So in this meaning, an observation of the tetraneutron state is very impacting for our community. And according to this experiment data, they reported the energy is like this. Now 0 MeV means that 4 neutron state breakup threshold. Okay, so then the energy and energies are reported by this resonance energy region to the bound state energy region. And gamma is a decay width is 2.6 MeV. This is the upper limit. So then, just I would tell you, so in this way, and such, and tetraneutron state has a so long history like this. So then so far they perform they performed such experiment for almost 50 years old, and but unfortunately it was so difficult to confirm the existence of this tetraneutron state. And so regarding this theoretical calculation, for example, so far around 20 years ago, they tried to study about the tetraneutron state. However, it was difficult to support existence of this tetraneutron state. However, this Stephen Piper also tried to calculate this system, and they suggested there would be possible to exist a tetraneutron system as a resonance state at the 2 MeV with respect to the 4 neutron breakup state. Threshold using the AV18 plus this kind of the 3 neutron state with green function Monte Carlo method. So then after that, and as mentioned before, 2016, that they observed this tetraneutron state, and they reported the energy is like this. Okay, so then after this and observed data, so many theoretical effort did this kind of calculation to reproduce the data or not. So first, I shall show you the positive result. So 2016, also 2017, the Shirokov and also Gandolf et al. And calculated the tetraneutron state using the non-core shell model for them and also quantum Monte Carlo method for them. And the interaction is different with each other. Then according to their calculation, they reported the energy is at 0.0 MeV with respect to the 4 neutron breakup threshold, and the decay width is like this. And on the other hand, the Gandolfi et al. Also calculate this kind of tetraneutron state. But so this calculation is not exact calculation, just extrapolation. And the energy, they reported the energy is a 1.84 MeV, and the decay width is around 200 keV. And also in 2017, another result are reported. They use a non-core shell model calculation plus this 3 nucleon force, and then so that they use they use this chiral potential and an interaction, and then so that they multiply some scaling factor to the NN interaction, and so they try to search where is a tetraneutron state. Okay, this is some F scaling factor, and this is the energy. And this 0 means a 4 neutron breakup threshold. And here is just observed energy. And you can see that, and here is a 1. This means no scaling factor. So then from the bound state to the some this one, and they try to explore this result, and you can see that finally they say conclude that energy is a 7 MeV with respect to 4 neutron state for the tetraneutron state, and also decay width is so the 3 MeV to the 4 MeV. So you can see in the case of the in comparison with the experiment data, and their reported energy is upper and decay width is more broader. So that means they say that maybe tetraneutron state still exists. However, and this energy is inconsistent with the data. So from this meaning, I would tell this result is not positive, not negative. However, and also we have a negative result. For instance, 2005, and so my collaborator and Rimantas Razaskas Carbonell already before an experiment, they calculate tetraneutron state. Okay, and they use the 4 neutron and potential. Then here this V is a W is a parameter, and changing this W, then they try to search the pole of the tetraneutron state. Okay, so if W is a very deeper, then they have a very big, they have very narrow and resonant state. You can see this real energy is this 0 is a 4 neutron wake-up threshold. Okay, and here is this resonant energy region, and this is the bound state energy region, and this imaginary part is a gamma. So you see, and the W is a sort of deeper, then we have a very narrow energy pole. However, if the W becomes so smaller, then the pole is moving like this. So then here is just W equals 0. Then you see, and they say that in the case of W equals 0, energy pole go to this third and third place. So this means that two body and an interaction does not produce any resonance state of the tetraneutron state. So this is their conclusion. And also, and after observation of the tetraneutron state, we published a paper and together with this collaborator. Okay, so then what about our result? I just show you my result. Okay, so then in order to calculate this result, also we use the NN realistic interaction together with the phenomenological 3-body force. Okay, and then in the case of the NN interaction, we use the Argon V8 NN realistic interaction. And also I use this kind of phenomenological 3-body forces. You can see that this is a two-range Gaussian potential, and here is W also in the parameter. Okay, and then this is in this case, and the total isospin 1/2 case, and we have this is a range part, this is an attraction part minus 2.48 MeV. This is a repulsive part. So in this potential already has been applied to the helium-4 total isospin 0 and ground state energy. Okay, and this energy, this and 3-body force plus NN realistic interaction is applied to the first helium-4 ground state. You can see that this is ground state of the helium-4, and this is second 0+ state. So using this 2-body and 3-body and potential, and you can see our result a good agreement with the experiment data. Okay, so then using this and 3-body potential, and also we apply to this tetraneutron state. Okay, and the tetraneutron state and the total isospin equal T equal 2. So then in this case, we need the total isospin equal 3/2 3-body force. But in this case, we use the same potential with this total isospin 1 of the helium-4 case, but different parameter of this W1. This means the attractive part. Okay, here is this repulsive part is just fixed, but this W1 strength should be adjusted so as to reproduce observed to tetraneutron state. Okay. So then in order to calculate this tetraneutron state and also hydrogen 7, so far we use the Gaussian expansion method, which is a kind of a variation method using the Gaussian basis function. And in this method, we take the old set of Jacobi coordinate, which has been developed by Kyushu University group, namely Kamimura and his collaborators, including myself. And this method has been high precision calculation of the various 3 and 4 body system, namely exotic atomic and 3 and 4 nucleon system, and so on. Okay, and in order to show up our result very accurately, so among the many and few body physicists, we had a benchmark test for this 4 nucleon bound state using the realistic NNAV8 prime calculation. Just I shall show you the result among all of the method of the Hugh-Body method. For instance, here is the FY means the Fadeev-Yakubovsky method, which is very well known in the world. And this is my result. And the third one is the stochastic variation method. And this is also green function Monte Carlo method and no-core shell model and hyperspherical harmonic and so on. And then this is also binding energy of the helium-4 case, and you can see our result, a good agreement among these 7 different methods. And also this is also the root mean scale radius of the helium-4 ground state. You can see also our result, a good agreement with each other. And here is NN correlation, and you can see just a solid line. That means our also result a good agreement with each other. So in this way, our result provide the good accuracy of the binding energy as well as this wave function. Okay, so but you see, and tetraneutron state, and if there exists, might be resonance state. So therefore, in order to obtain the energy pole, namely energy together with the decay width, we should use another method. So in this method, I use a complex scaling method. So that means that here, and we use this, and in order to calculate four-body system, we use this two kinds of Jacobi coordinate. And then so in this each coordinate, we use the Jacobian coordinate and also a Gaussian basis function. And here, among the Gaussian basis function, we are scaling parameter. We use a scaling parameter I theta, and then for each coordinate, we scale. And then theta is just a parameter, just angle. And then so if theta is angle, and after diagonal Hamiltonian, we can get this energy pole. And if theta is just scaling, then this energy pole is scaled like this. And the continuum state is just moving with respect to the scaling parameter theta, but the energy pole is stable with respect to the theta. This is a pole. And then here, for instance, we get the energy and decay with as following. Here, we assume that 0 means a 4 Newton breakup threshold, and here is a 6, and this is the energy. So you can see, in this case, we have energy is a 6 MeV with respect to 4 Newton state, and also, and this is imaginary part, so divided to 2. So therefore, here is a 3 MeV and gamma. So therefore, in this case, imaginary part is a minus 3 MeV. So therefore, gamma should be multiplied 2. So therefore, the decay width should be 6 MeV. So in this way, we can get the energy pole. So then, and just changing the W1, we try to get energy trajectory for the J equals 0 plus state like this. Okay, so here is a 4, and this solid line is a 4 Newton breakup threshold. Okay, so then here this energy region is experimental energy region. Then this blue number is a W1 number. So then And in order to get and reproduce the data of the tetraneutron state, then the so W1 should be the minus 36 to the minus 30. However, if this W1 is the decreasing like this, then energy pole is and moving like this, and then just so in comparison with experiment data, and energy pole is far away from experiment data, and the decay width and become more wider. So then also in order to show up more clearly about my result about tetraneutron state, and we can see like this. Okay, and then this line is the number of the W1, and then this is also energy. And then 0 mean again, and 4 Newton breakup threshold. And the energy pole is like this, and this red arrow is the energy region. So then if we have the minus 36 to the minus 30, and we could reproduce the data like this. However, if we have a very small number of the W1, and then energy pole become far away with respect to 4 Newton breakup threshold, and decay width more become more wider. So then let's talk about this number of the W1 is reasonable or not. Okay, so then in order to obtain the energy of the ground state of the helium-3 and helium-4, then this W1 for this and the T+4n state should be minus 2.04 MeV, okay, very small value. So then just so we can compare this value to the minus 36, 30. You can see that the attraction is 15 times stronger than this value. Okay, so then this value is for this T+3 is reasonable or not. So to check that this validity of the 3-body force, we can calculate energy of this hydrogen-4 and helium-4 with isospin 1 and lithium-1 case. Okay, so then in the case of hydrogen-4 and lithium-4, already we have an experiment data. This is experiment data. So then these ones are the lowest threshold of the triton plus neutron. So this with respect to this lowest threshold, and ground state of the 2- state of the hydrogen 5 is above, and the energy is 3.19. That means a resonant state. And you can see this is a gamma, and you see, and this resonant state and decay width is very, very wide. And also in the case of lithium-4, is and due to the Coulomb interaction, energy become more and far away than this hydrogen-4, and also decay width is much more and broader. Okay, so then using the question is if we use the minus, so this W1 minus 30 to the 30 MeV, and to reproduce or observe data on tetraneutron state, what about the binding energy of this hydrogen-4 and helium-4 and lithium-4? Okay, this is my result. Okay, and but we should be careful, and it is notice that this lithium-4 and hydrogen-4 just a resonance state. That means this is also the lowest threshold. Then with respect to this lowest threshold, experiment data should be above. Okay, and then so just I show you that if we use this W1 to the minus 36, 30, and you can see that all results are deeply bound state with respect to this lowest threshold. So then if this result, this W1 is more and becomes so smaller, then like so the minus 20, then almost and the critical point to bound or unbound. Okay, so then from this result, and we can see this result is inconsistent with the data of A-4 nuclei. That means the 2- state of the helium-4, A-4 nuclei should be resonant state. However, in this way, in order to reproduce a tetraneutron state, that's we need this area that means we have a very deeply bound state. So then in this way, conclusion is following. To reproduce the data of the tetraneutron state, we need unlikely attractive three-body force. And also the same conclusion done by Del Tuba. They use the Faddeev-Jakubowski method, and they use the SRG potential, which is based on AB18 the potential. In this case, he multiplies some factor to the NN interaction of this and the singlet S0. So then, you can see that, and this is a scaling factor. Then if we have a very large scaling factor, like a large scaling factor, then we have a bound state. However, if so, also their scaling factor should be decreasing, then the energy of the tetraneutron state is like this. So then finally, and this pole is disappeared. So this is a conclusion by Del Tuba. So therefore, they have a negative result. That means they have a no pole for the tetraneutron state theoretically. And also, very recently, 2 years ago, when they Piggy and so on calculate the tetraneutron state using the hyperspherical harmonic method using the AB8 potential, which is the same one used by me. And then they calculate the phase shift analysis for the tetraneutron state. You can see that energy is like this, and the phase shift is very small, almost zero energy. So that means, and he had also concluded that no resonance state. Okay, and also they use another potential, namely AB18 potential. But also, even if they use the AB18 potential, and they had no resonance state. So therefore, this is a summary of the theoretical calculation. Now I already introduced the two kinds of the positive result by Shirokov and Gandolfi, but after that, they forces calculate also tetraneutron state. In this case, they have not positive, not negative result. However, almost many authors say that negative conclusion, including myself. Okay, so that to me, the AB8 and AB18 potential give the negative result, namely no resonance state. So then and in this way, now we have the negative result. So, but after now theoretically, now we come to negative conclusion. That means no resonance state for the tetraneutron state. However, just so in the last year, also again, the experimentally, this is the Nature and Physics, they reported the experimentally tetraneutron resonance state has been reported. So now, maybe it is time to consider this part theoretically again. So therefore now, even if we tune the nuclear-nuclear interaction, theoretically it is difficult to reproduce the data. And also, in order to investigate this tetraneutron theoretically, maybe this is my idea. In the case of the tetraneutron state, let's add it one proton. This is hydrogen 5. And also, we can add it to triton cluster to this and tetraneutron state. This is hydrogen 7. Okay, so then in this case, and you see neutron number is 6 and proton number is 1. So therefore, hydrogen 7 is like a super heavy hydrogen. So then we have a question. This hydrogen 7 is bound or resonance state or nothing? Okay, so let's explain about hydrogen isotope before talking about hydrogen. So what is interesting to study the hydrogen isotope? Of course, in order to study about tetraneutron state and hydrogen isotope is a very useful system to think about it. But also, following reason and hydrogen 7 is very interesting. Okay, and then hydrogen is the lightest isotope in nuclear physics. So you see, and these are the experiment data. Okay, and everyone knows about deuterium is a so bound state, and also one of the lightest in a nucleus in a non-strangeness nucleus. So the binding energy is a minus 2.2 MeV, and also we can put one more in a neutron, and this is a triton. And the ground state is a 1/2 plus state, and ground state energy is a minus 8.48 MeV. And as mentioned before, also I can and we can add it one more neutron, and this is the hydrogen 4. But in this case, also this is experiment data, and in this case, the ground state is 2 minus state and the resonant state, and the energy is like this, and the decay gamma is 5 MeV, is very broad resonance state. And just 20 years ago, hydrogen 5 has been observed. Okay, and in this way we can put on the hydrogen one more neutron. Okay, so then according to this experiment data, they reported the energy is like this. This is a resonance state, and with respect to the triton and the 2 neutron breakup threshold, energy is 1.7 MeV, and the gamma is close to 2 MeV. Also, we call this hydrogen 5 system as a super heavy hydrogen. And however, and just I show you the recent experiment data. However, also after this observation, there are several experiment data. So these are the list of the experiment data, and here is the energy, and this is the decay width. So you see that, and almost this energy is similar with each other. However, decay width is a very variety of like this. So, but maybe and we take this value. However, just so I remind you, in this way, this energy is almost 2 MeV, but decay width has dependent on the experimental data like this. So then, in the case hydrogen 7, also, and in the 2017, also we have a new data on the hydrogen 5 by Alan Uzma, and they reported energy of the hydrogen 5 is around 2 MeV, and the decay with 5 MeV, which is very broad resonance state. So in any case, in this way, decay width is strongly dependent on the experimental data. Okay, so then what about hydrogen 6? In the case hydrogen 6, we have several data, but unfortunately, no confirmed data of hydrogen 6. So then let's move on to hydrogen 7. Okay, so then in this case, number of the neutron is 6 and proton number is 1. Okay, and also 2003, and Korushenik et al. Reported the evidence and indication of the hydrogen 7. However, according to this paper, they did not report any energy and decay width. And 1 year ago, 1 year later, in Camargo et al. And also performed the such experiment of the hydrogen 7. And then they reported the energy is like this, and then with respect to triton plus 4 neutron breakup threshold, and the gamma is very narrow. So then we have a question. Now, and experimentally, they observed the hydrogen 7, but what is the end of the hydrogen isotope? Okay, so you can see that this hydrogen 7 is according to this Companion data is very close to this threshold and decay width is very small. So therefore, if this energy, this experiment data is true, then maybe we could have a heavier hydrogen isotope such as hydrogen 9. So therefore, also we have another question. What is the limit for the hydrogen isotope? Probably hydrogen 7 or further. Also, this is also a question. Okay, so in order to answer this question, and theoretically, and several authors try to calculate hydrogen 7. Okay, I will explain about this theoretical calculation. First, 2002, Timoth et al. Calculate that this hydrogen 7 and using the hyperspherical harmonic method, using the Volkov NN potential. And this is the surely 5-body and 7-body calculation. And she reported the energy for the hydrogen 5 is 1 MeV above the triton plus NN breakup threshold. And in the case hydrogen 7 is also 3 MeV above triton plus 4N breakup threshold. But so that means above this threshold, this means that these are the resonance state. But she calculated energy with bound state approximation. So therefore, she did not give decay widths for these two nuclei. And after that, Aoyama-san and Itagaki-san calculate lithium-7 again using the same interaction like Timoth's calculation. But their framework is AMD calculation. And this also they reported the energy of the hydrogen 7 to be 4.2 MeV above the triton plus 4N breakup threshold. However, also, and they use the bound state approximation. So therefore, they did not give any decay widths at that time. And also, they did not report for the energy of the hydrogen 5. And 2 years ago, Lee-san calculated the also hydrogen 7 nucleus using the Gamow shell model calculation using the Minnesota NN potential. And according to this calculation, and they predict the energy and decay width of the hydrogen 5 is 1 MeV and decay width is 500 keV respectively. And also on hydrogen 7, and they predict the energy and decay width is also 3 MeV for the energy and the decay width around 100 MeV, which is very shallow resonance state. So in this way, they predict the very narrow decay widths for the hydrogen 5 and hydrogen 7. Okay. So then also, and just recently, and at the RIBF factory, and this reaction has been done at the RIBF factory. And this is a proposal number, and the analysis is still ongoing. So therefore, also it is timely to calculate the hydrogen 7 to obtain the energy and decay width theoretically. In this way, motivated by this situation, and then we studied the hydrogen 7 structure within the framework of the triton plus 4N 5-body problem. And also we also discuss on the energy and decay width of hydrogen 5 within the triton NN 3-body problem. Okay, so then this is also my framework. And also we use NN potential. We take the Minnesota potential, namely central potential only. And in the case of triton and Newton potential, there is a large ambiguity. Okay. So then we use the several data for the phase shift of the triton and Newton case. So then for this term, we use this kind of the potential. Okay, this is in the central potential, and here is and like a OCM potential. That means that 0S is a forbidden state. So therefore, that this lambda should be in some larger number. At this time, I took the 10 to the 4, and maybe it's also the very large number. So therefore, the Pauli forbidden state is taken on far away, like this. So then you can see that also this toroidal neutron potential is also fixed. The parameter is so that this also phase shift and also any cross section, which I show you in previous pages. Okay, and this is also the calculation using the Marfrig-Chon potential for the four-body just calculation. And you can see 1 minus in the S equals 0 and the spin equals 1 case. And you see that so that these are the energy position and the decay width. And this two-body potential of the Tn is almost consistent with this four-body calculation. So then using this in the Nn and Tn potential, and also further I introduce a phenomenological and three-body Tnn force to obtain the energy trajectory. You can see that this V0 and this is a range. Range is we take this kind of ranges, and here we take the V0 and this range V3 is a parameter. That means these two parameters is fit so as to reproduce the data of the hydrogen 5. Okay, now I apply to these and interaction first hydrogen 5. Okay, and as mentioned before, like a tetraneutron state, and then so hydrogen 5 has also resonant state. So therefore, we use a complex scaling method. Okay, so however, I remind you, as mentioned before, the experiment data has several experiment. We have several experiment data. That means energy is like this. However, decay width is also like we have a very variety of this decay width. So therefore, we are not sure which data I should fit the hydrogen 5. This is my question. Okay, so therefore, and next, and in the case hydrogen 5, this is a 5-body calculation. So therefore, it is possible for us to calculate 5-body calculation. So therefore, using the several NN interaction, we try to calculate hydrogen 5 theoretically. You see, this is our result. So then here is also the energy of the hydrogen 5, and this is the decay width. So then you see, independent on the NN interaction, and our results are an energy of the hydrogen 5 is almost 1.8 MeV, and gamma is 2.4 MeV. So therefore, we take this result as an experimental data. However, in comparison with our result with experiment data, and 20 years ago, this Kolesnikov data is very close to experiment data. This is surprising. So then this is the energy trajectory hydrogen 5. Okay. So then as mentioned before, V0 and B is just a parameter. So then in order to reproduce the data of the hydrogen 5, we try to search the best fit of the V0 and B. Okay, so then you can see that this blue dotted is and B3 is 8 femtometer, and this red point is 7 femtometer. And then this black point is 6 femtometer. So then here is so this blue green line is a Kolesnikov experiment data. And then here is this blue, this point is an experiment like and the theoretical value calculated by us. Okay, and it's a 5-body calculation. So then comparing with this green and this and this blue, then you can see if we take the B3 equal 8 femtometer, then so it is close to this experiment data. Actually, and the V0 equals 3 or 2.5, then the energy pole of the hydrogen 5 is close to the experiment data. So then we have a question. If we have this potential parameter, then what is the energy pole of the hydrogen 7? Okay, So then in order to calculate this and hydrogen 7, this is a 5-body calculation. Then we take the many kinds of the Jacobi coordinate. For this calculation, totally I use the 120 Jacobi coordinate. Among them, this coordinate is very important coordinate to get the energy. So this is the channel of the hydrogen 5 plus 2n and coordinate. And this is the wave function of the hydrogen 7. Okay, this is the isospin wave function, and this is a spin wave function and the coordinate part. So then actually the coordinate part, we take the like this. So then each coordinate, we use the Gaussian part as for the radial part like this. And here is this Gaussian, is this Rn is just Gaussian range. And then R1 is, and we take this Gaussian range taken as a geometric progression. So the R1 is in the first part of the Gaussian, and this ratio, and in n is a number of the base function. These three are the just parameter. So in order to get the energy very accurately, we try to search this and the best fit of the parameter. And similarly for the other bases, for the capital R and rho and S. So then the use of this type of the Gaussian basis function is known to be very suitable for the describe simultaneously both of the short-range population and long-range behavior of the Hughes body system. Okay, so then using this kind of the basis function, and in order to solve the Schrödinger equation, we should diagonal Hamiltonian. So then after diagonal Hamiltonian, we obtain n eigenstate for the each J pi. So then now, and for the hydrogen 7 and ground state should be J equal 1/2 plus state. So then now here, currently we use a 15,600 basis function. So therefore, after diagonal Hamiltonian, we obtain a 15,600 eigenstate function of the J equal 1/2 plus state. For the calculation, for the calculation resonance state of the hydrogen 7, it is difficult to apply the complex scale method for the 5-body calculation. So then for this calculation, and I use the real scaling method. What is a real scaling method? This method has been often used in atomic physics. In this method, we artificially scale range parameter of our Gaussian basis function by multiple factor alpha, okay? And the alpha scaling parameter, and for example, we scaled the alpha to the 0.8 to the, for example, 1.5. And for each alpha, we repeat diagonalize, repeat the diagonalization of the Hamiltonian. And then this is a schematic illustration of the real scale method. So if the range parameter, this is the range parameter of alpha, and this is the energy. Then for each alpha, we diagonal Hamiltonian. Then with respect to scaling parameter alpha, and if we have a non-resonant continuum state, and this state should be decay into the some threshold. However, resonance state is just a physical value. So therefore, this resonance state should be stable with respect to the scaling parameter. For instance, this is just the example, and then for the scaling parameter. Okay, this is alpha and this is energy. So this point is also energy pole. Then each alpha, we diagonal Hamiltonian. Okay, so then if, for instance, in the case of alpha equal 1 after diagonal Hamiltonian, we can get this value. Okay, and then we plot it for each value. So then in this case, and the continuum state is decay into the some threshold. However, And if we have a resonance state, in this way, we can have very stable. So then in this way, we can distinguish the resonance state or a continuum state. So we apply this scaling method to the hydrogen 7. So in the case of the hydrogen 7, among the many and the Jacobi coordinate, and we scale to this part and this part. Okay, this is our result of the hydrogen 7. Okay, so then in this case, we use the B3 equal 8 MeV and so on. So then you can see, and with respect to the scaling parameter alpha, then we have this in like a red, and we have a very stable state. Okay, so this energy is with respect to the triton plus 4n breakup threshold. So then from this real scale method, we can get energy should be 8.8 MeV, and the gamma is around 3 MeV. Yeah. So then also we try to calculate trajectory of hydrogen 7. Okay. So then together with hydrogen 5, as mentioned before, if we use a B3 equal 8 femtometer, then this result is close to hydrogen 7. Then if we have a 2.5 MeV, just we reproduce the data of the hydrogen 5. And if the SOSA and V0 and is increasing, and we can get the narrow resonance state. Okay. So then if we have a 2.5, and what's happening in hydrogen 7? Okay, here it is. This is my result. Okay, so then if we use a 2.5 energy, and the decay energy is a 9.5, and then gamma is almost 3.5 MeV. So then the energy, you can see that energy is more far away, triton plus 4n threshold, and the decay width predicted to be the larger. But also we use the larger value of the V0, then the energy should be close to the triton plus, this 0 means the triton plus 4n breakup threshold. So then this larger value of V0 and energy close to the decay threshold of the triton plus 4n, and if we have 7 MeV, then we have a bound state. Okay. So then as far here, from this figure, we can say, as far as we believe that the energy of the hydrogen 7 as experiment data, then the energy of the hydrogen 7 should be much far away from the triton plus 4n, and the decay width is larger. And this is summary of the hydrogen 7 isotope. Okay, and then this is a triton, and this is gamma, and hydrogen 7. Also, we reproduce this data and hydrogen 7, and even if we have no data, but we could calculate the hydrogen 6 like this, and this is hydrogen 7. Then you can see that the triton plus 4n threshold, this energy is much far away from this breakup threshold, and gamma is so larger. So therefore, if my result is correct, then maybe we would tell is hydrogen 7 might be end of the hydrogen isotope. So now this is a conclusion and summary, and assuming that this energy of hydrogen 5 is like this, then our calculated energy and decay width on hydrogen 7 are this 8 to the 9 MeV, and the gamma is 3 or 4 MeV. That is much higher than the hydrogen 5 plus NN threshold, and also we have a broad resonance state. And as mentioned before, that this reaction experiment was done at our RIBF factory, and then this analysis is still ongoing. So then this result will be maybe reported by someone soon, and I'm waiting for the further and experimental result. But so if so, what's happening about the tetraneutron state? So finally, I would have some comment on this state. Okay, so then recently, I just tell you the I would tell you the like this. Okay, and in order to produce a 4-neutron state, and the proton hit this helium-8, and then after that, this 4-neutron is just remaining, and helium-1 proton is a knockout. So then and this is simple our comment. Maybe by finite state interaction, then this 4-neutron state seems to be exist. So then, for instance, we use this and wave function of the continuum state in tetraneutron state, and this is the initial function, and then just we calculate this reaction cross section, and this is the data, and also we have just a continuum. If we use just a continuum state, tetraneutron state, no resonance state, but we could reproduce this data. So therefore, in our opinion, it is difficult to exist in tetraneutron resonance state. So then maybe future experiment in hydrogen 7 and hydrogen 5 give final answer to us about tetraneutron state. Okay, thank you for the attention.
Okay, thank you very much. So Professor Hiyama's nice talk. So since Professor Ma has another meeting, so I take charge of the discussion section. So now the seminar is open for discussion. So if you have any question, please raise your hand or just mute and just ask.
So, can I ask a question? This is Zhang Hunyang from Peking University.
Yeah,
hi, Hiyama-san. So first, I'm very happy to hear your recent results on tetraneutron and also the hydrogen 7, of course. And also thanks for introducing our experiment. First, I want to say that we have some progress since our last discussions, and probably we'll soon come to some nice results, I hope. Maybe for your talk today, I have several questions, if time allows. So first is, I'm interested to hear your opinion, like, so now you calculate hydrogen 7 in kind of a picture of triton plus 4 neutron, and finally we can determine the resonance energy, the weight, and also the spin parity. So then we understand still it's very exotic. Can we still understand in the shear model picture, like how about the occupation of these 4 neutrons in the single particle orbits from your calculation?
No, in my calculation, it's just a hypothetical calculation. So therefore, it is quite difficult to share model picture. But so that maybe if you want to think about the shell model picture, that the 4-neutron state is the 2 particle, 2 hole, and also we can just excite more particle. Right? Automatically, I can include the much higher. So that this and orbit in terms of the shell model calculation. That is why our calculation is very, provide very accurate calculation.
I understand.
So therefore, my result should be quite different with the shell model picture, because the shell model picture they just limit the orbit and occupation orbit, right? So therefore, in principle, even if they use the shell model picture, if they could obtain many higher partial wave, then my result become consistent with mine.
Oh, I understand.
So therefore, my result automatically and easily and excited very higher.
Okay, so maybe still I have another short question here. So in that, some people thinking about the n equals subshell closure even in hydrogen 7. So from your opinion, this may not be the case here in hydrogen 7.
No. So then the mainly dominantly so like this. However, I never saw that restrict any configuration. So that is why, and I have many configurations at this time. Then if so that you want to see that, maybe I should just so that calculate some, and reduced amplitude. But so that I will tell you again, but so that the problem is my calculation is so the wave function is broad resonance state. So therefore, I'm not sure which and wave function I should obtain. If my this wave function should be if we have a very narrow resonance state, it is possible to get the wave function very easily. But in this case, it's broad resonance state. Therefore, it is difficult to calculate something so that reduced amplitude using the wave function because no wave function.
Okay.
You understand?
Probably you already answered my second question, but still I want to speak it. So my question is, since you have the 5-body calculation, in my naive expectation, you have the wave function. Then I'm wondering if you can say the kind of this correlation between the 4 neutrons. From experimental side, we can measure the correlation, and then we can see something about the structure. So if you have 5-body calculation, you can provide the correlation. Then I think that's very helpful when we comparing the theory and the experimental data. Yeah.
Okay, so that was mentioned before that at this time, unfortunately, my result is a very broad resonance state. Therefore, it is difficult to get the wave function, unfortunately. And you can see that this is a 5-body. Okay, here also okay, like this. Okay, so this is a resonance state like this. This is just a pole. But if we have just around this region and this narrower, then easy to get. Calculate the wave function, but and it is difficult. So then, if so, Yan-san has also provide very shallow resonance state. Then maybe this point, then I can get easy to the wave function, then easy to calculate the correlation function easily. But the problem is so that if I believe that the energy region is like this, then energy is like this. But as mentioned before, even hydrogen 5 and decay width it has a very variety. So therefore, now I just believe this point.
Okay.
So then also I have a question: which part I rely on the data of the hydrogen 5? That is why I put on this energy trajectory together with trajectory.
I think at some point you mentioned there are some ambiguity for this hydrogen 5 state, I remember. So from experimental side, if this is indeed something important for theory calculation, of course, we are interested in providing more current data. Yeah.
Yes. So this is the data. Actually, I would tell you again, hydrogen 5 is very, very important. And actually, in the energy already fixed, this is okay. However, decay width is very important because the decay width is related related to the wave function of size of wave function. So that is why I need the imaginary part. Then if you can see, if the decay width is so lower, smaller, then quickly the hydrogen 7 is close to this 0 threshold. Then I can get the wave function very easily. So that is the point. So therefore, also hydrogen 7 energy is very important, but also hydrogen 5 and the measurement of the decay width is very, very important.
Okay, so maybe a last question. Yeah, sorry. So it's still, I mean, let's say for hydrogen 7, I think your energy is high and broad, but you emphasize like it's a resonance, right?
Yes.
Okay, that's a very important.
Yeah, but also we have a bound state like this. Even so, we have this 7. You can see this is bound.
Okay.
So then if we have a very close to 1 MeV for the hydrogen 5 and the decay width is very close to just so and 200 kV, it's bound.
Okay, spawned even more interesting. Yeah, okay. So this situation is very, very different from tetraneutron case, right?
Yes, very different because triton is so we have a very attractive interaction. So therefore, the the tetraneutron, in order to reproduce the data, I need the phenomenological three-body force, but we need so very strong attractive. So that means and if so and tetraneutron should be compacted, we need some strong attraction. Triton should be like this. And also alpha particle is like this. So that is why helium-8, alpha plus 4n, we have a bound state.
Okay.
Yes.
Okay. Thank you very much. And also, I hope this year we can somehow meet somewhere in China. Thank you.
Thank you. So yeah, I saw that Xiudong Laoshi has a question, but before we give the phone to Xiufeng Laoshi, let me try to also ask, because I probably know, I have a question, but I probably know the answer from the discussion you and Zai Hong. So please allow me to say it again. So can you go to the framework of your hydrogen 7? So you list you have 120 Jacobian, but actually your result, let me try to repeat if I understand correctly, because you state your result is solely related on this hydrogen 5 this configuration on the top right. So my question is that, so the hydrogen 5 which actually suffer very large uncertainty from experimental measurement, and so how can you consider the large uncertainty into the calculation? Yeah, you probably just discussed it, because when you have the trajectory, actually, so if is that correct that if the measurement is go to the different value, so this will go to the hydrogen 7 also will change your results?
Yes. So you mean yes, and yes. So the ambiguity is just a potential, okay, and then. You see, I just give you the trajectory of the hydrogen 5, okay, here like this, okay.
Yes,
so that so simplicity, I just show you the result of the hydrogen A and B3 = 8 pentameter, okay, because this point is very close to the data. But if we have this kind of red and black, then also result of the hydrogen 7 should be changed. Okay.
My question is that because you just pick one data.
Yes, no, two data. This one. You see this one and this data. Okay, this is my result, just a theoretical calculation of the hydrogen 5 we use. Because I just tell you, okay, because why? Okay, this is the calculation, 5-body calculation, okay, and using the various NN interaction. Because if we put on only experiment data, then you can see the experiment data has a many variety, okay, especially the decay. So therefore, as mentioned, you are correct, because so that I'm not sure which data I should rely on. Just so I choose this one. However, so that is why, and in order to rely on the data, finally I calculate 5-body calculation using the various NN interaction. And this is my result, energy and decay width. Okay, and you see that energy is like this, almost 1.8 MeV, which is independent on the NN interaction employed. And the decay width is 2.4 MeV. So therefore, we take this result as a data at this time. So therefore, we decided to use this blue line, okay?
Okay.
Then this red and black just exclude. This is my idea.
Oh, I see. Okay. Thank you. Okay. Thank you. So, thank you. So, Xiudong Laoshi.
Hello there. Can you hear me?
Yes, we can hear you.
Yes.
Excellent. I want to ask you from different angles. So as a baric analog state, isobaric asymmetries seems to be robust. So my question is, you discussed hydrogen-7. Is your method can be applied to other A=7 isobaric system like helium-7, lithium-7, barium-7, boron-7, for examples? And what's the predicted powers? What are the analog states in the isobarical nucleus?
Okay, thank you very much for your question. But at this time, and so far, I applied to the lithium and helium-6, and also helium-6 and lithium-6, and so on. And but so unfortunately, the result should be independent on the potential Hamiltonian employed. So therefore, once I calculate the potential and then interaction, then I just tell you, I can give you some energy, pole, and also energy, eigenvalue, and also wave function, and very precisely. However, if we focus, we try to compare with my result with experiment data, then ambiguity always comes with potential. So that is a point. Is it answer to you or not? That is my answer.
As an experimentalist, I always looking for robust theory. So you use triton plus 4 alpha as the approach for hydrogen-7, right? So I wonder if you can further explore, so you can describe the entire A=7 as a barrier chain, and also identical this kind of a analog state in other systems.
Okay, so then this is my answer to you. Okay, in order to show up my prediction, always I focus on the subsystem. That means that, for instance, hydrogen-7 case, before going to hydrogen-5, always I should be careful about subsystem. In this case is hydrogen-5, right? And if that my result is good agreement with hydrogen-5, and hydrogen-7 should be predictive. So in this meaning, for instance, and hydrogen-6 and another system, I try to attack such kind of idea. And also, I'm a hypernuclear physicist. Always I should be careful about such kind of idea. So that means always I should be careful than subsystem. So therefore, always in hypernuclear physics, and my result before, always I predict my result before experiment. Then my result always in good agreement with the data. So therefore, always on subsystem it should be important. So something along this line, and then even in the boron isotope, and this is my now future plan, then so that my result should be predictive. This is my idea. How do you think?
Oh, I understand you. Yeah, thank you.
Okay, so thank you. And next, Guoqiang.
Okay, thank you. Hi, Professor Hiyama. I have a question about, you just talking about the interaction. When we calculate Lowe's bound state, two-body interaction favor the bound state. But three-body interaction seems to tend to be unbound or repass the nucleus each other or reduce the binding energy. But in the case of the resonant state, they are above the threshold or they are unbound. So I cannot understand why you say two-body interaction do not favor those resonant state. As you just mentioned, from all the models you provide just now, you say you need a three-body interaction to get the resonance states.
You mean that's also why I need this three-body resonance, three-body potential? You mean?
Yes.
Okay. Yes. because if we do not use any 3-body forces, and then only I use a 2-body potential, then this is also the calculation of the hydrogen 5, you see? Okay, even if so, that if we do not use any of this 3-body force, then the energy should be far away from the experiment data. That to me, that if we assume the hydrogen 5 and as a triton cluster plus NN, and this is a model, then I didn't taking account of the blocking effect of the triton or excited effect of triton. Okay, this is a model. So therefore, this 3-body and the potential origin comes from the blocking effect of the triton. So that is why I need this 3-body force. Okay, so therefore, please do not confuse the origin of the 3-body force. Sometimes, if we focus on this only nucleon case, the 3-body effect and origin comes from the Fujita-Miyazawa type. But this is not the case, because I just assume the triton cluster.
Triton.
Yes. So therefore, once we assume some cluster, then we didn't take account of any excited effect of the cluster.
Okay.
Then if we need this kind of effect, always we need 3-body force like this.
But your 3-body is the combination or the possibility, including the triton and the triton with another neutrons.
Yes. So therefore, the triton and this is then due to the NN interaction, the triton should be excited. So that is why you see this is just a 5-body. So in this case, I do not assume anything triton core. Just I use NN interaction. Then you can see our result is like this, which is independent on the NN interaction. This is the reason. However, once we assume the cluster, then we couldn't reproduce such kind of state because model. So therefore, I sacrificed the excited effect of the triton. That is why, this is a model. In order to reproduce this data, then we need this phenomenological 3-body force. That is my reason why I introduced this 3-body force.
Okay, thank you.
Thank you. So let's move to next, Wang Laoshi.
Professor Hiyama-san, thank you very much for your very nice report. Here I have several questions. First is that when you mentioned that your previous work about the terra neutron systems, and you try to add triplet channels 3-body force, and you add W1 and W2, and you said W2 is the same, but you change the W1 case. And I noticed that W1 seems to be an attractive potential, and W2 is a repulsive potential.
Yes.
Yeah. So after your calculation, you find that you need very much more attraction, so that you can get the resonant state. So here I want to know, did you check that whether you have changed the W2 case, because W2 is a very large, relatively large repulsion. So
Okay, thank you very much for the good question. I did already. I changed this balance of this change W1. However, unfortunately, even if I change, for instance, this W1, W2, maybe any larger or smaller, and of course, if if I change the double one and also double two, if I change the double two value and the double one also and change. However, even if so, and this kind of the trajectory you see, and of course a little bit changing, but and my conclusion is no change, has no change. That means that even if we try to reproduce this data and attractive part, more should be the much larger. That is my conclusion is so the same. This is my answer.
Yeah, thank you very much. So that is to say for the terrestrial system, they need to add much more attraction.
Yes.
From the three-body case. Actually. Thank you. The next question is about your calculation about the hydrogen 7. Here you added three-body force about triton, neutron, three-body force. So yes. in your calculation, did you consider three nucleus force?
Okay, I see. Thank you very much for the nice question. Okay, and also I wanted to include such kind of things. However, and currently I did not include anything about three nuclear forces because now I just saw that give to experimentalists this my result. If the data of the hydrogen 5 and the decay with confirm, then for instance, like this, okay, if the sort of this assume the energy of the hydrogen 5 experiment data confirmed like this, then and hydrogen 7 data is like this, then so you can see much different with this, for instance. So if so, we conclude maybe we need the three neutron forces like this. So then I need to the experiment data. Otherwise, I couldn't get any three-body forces at least. So that is why now currently, and I did not include the three neutron forces. That is the reason why. So therefore, I'm waiting for the result of the hydrogen 7 together with hydrogen 5.
Yes, thank you very much. Actually, we also expect the new experimental data. Thank you very much.
You're welcome.
Okay, thank you. So any other question? Yeah, Chongwu.
Hi, Professor Hiyama-san. Thanks for your nice talk. I'm just wondering about other excited states of hydrogen 7. Since 3/2 and 5/2 states are suggested in recent experiments. So I'm wondering, have you calculated them?
Oh, okay. And unfortunately, currently, I didn't so calculate any excited state hydrogen 5. But surely, I expect that there is an excited state, maybe in a three half-plus state and a fifth half-plus state, right? Am I correct? Right. Yes. So then so first, I need to fix the position of the ground state hydrogen 7. Okay, if it is far away and hydrogen 5 is an excited state is more far away. So if so, technically for me, it would be difficult to calculate this state, right? Because so far away from here. So then if this state is more lower, then so it's possible to calculate hydrogen 5 and hydrogen, and 3 half state and 2 half plus state like this. So therefore also that I need to wait for the experiment data. But thank you very much. Yes, once so the experiment data and the ground state fix, immediately I would calculate the excited state of the hydrogen 7.
Okay, thanks for your answer. So can I ask another question?
Yes.
As in your introduction part, you gave a picture about insert one proton or triton to the 4-neutron system. So,
yes.
Can you give a comment about the maybe for possible for neutron correlations in a finite nuclei. Yeah, because you provide a weaker attraction from maybe the solid triton. So what happens to the four neutron system? Maybe about the correlation strength of these four neutrons.
And what about it? Because in the case of tetraneutron state, I don't have any resonance state. So therefore, it is difficult to calculate some correlation function, right?
Yeah.
So
yeah. Yeah.
I can understand what you mean.
Yeah. I just wondering if you can give a comment about what happens to the tetraneutron system when you insert solid proton and a solid triton cluster. Yeah.
Okay.
Yeah.
Okay. Yes. So then if this is my comment. Okay. So if the tetraneutron state exists, then the one proton is added. Then hydrogen 5 should be immediately bound state.
Okay.
Yeah. So then but unfortunately, hydrogen 5 has no bound state, only resonance state. And if we believe the current data of the hydrogen 5, then the decay width should be more broader. So then it is difficult to put on. So that means that in just tetraneutron state, this is my answer. Tetraneutron state unfortunately does not exist. This is my comment.
Oh, okay. Thanks for your comment. Okay.
So if may I also comment here? If it exists, then probably that is not triton neutron, right? That is another cluster.
Yes, that's right.
Yeah. I have one last question. You have also calculated the hydrogen 6, but you actually didn't mention the detail. So
yeah.
I'm asking that, because the hydrogen 6, so the mass and the width from the calculation, can you? Yeah, I'm asking because our students are working closely with Professor Joseph Pachdala at Mainz. So they are trying to perform the hydrogen 6 energy measurement experiment. So they have prepared for a few months. They will continue in the new year. So I want to hear your comment on the hydrogen 6.
Okay.
So
yes.
Because the energy in your calculations, the hydrogen 6 is very high. So I'm asking if it is also relied on the hydrogen 5 data.
Okay.
In your calculation.
Okay. So the hydrogen 5 is like this, but the hydrogen 6 is just jumping. Why? Because you see, in this case, triton cluster plus 3 neutron. Okay. And then just unfortunately, and so around the triton core, a 3 neutron, and the correlation is always 2 neutron correlation is important. So then this is 3 neutron, then the 2 neutron is a pair, but the 1 neutron is remaining. So therefore, this is very unstable. Okay, so that is what energy you can see is so that it's little bit higher than hydrogen 7. Hydrogen 7 is so we have a 4 neutron. So therefore 2 pair correlation. So therefore due to the correlation, therefore energy is lower than there. But here you can see this is the dineutron, triton plus dineutron. This is more stable. So therefore from here 3 neutron just jumping. So therefore in the case hydrogen 6 more unstable than hydrogen 7 to the hydrogen 5. This is my comment, and the result is like this. And the decay is much wider.
And the decay width so let me try to ask a little bit. So the decay width of the hydrogen 6 also is very large compared to the hydrogen 5 and 7.
That's right.
So is that also connect to the picture that because you say that there's 2 neutron interaction, that 2 neutrons is a pair, and one third neutron actually is just very loosely outside. So will this also affect the width?
Yes, that's right. Yeah. So therefore, in this case, so very, very unstable. That is why decay was so larger. Unfortunately, of course, technically, it was so difficult to get that this decay was because these are so wider.
Okay. Okay. I see. I see. Yeah, we will try to perform this measurement.
Yeah, if you can obtain this result, I'm very happy. Then so I can compare my result with yours. I'm waiting for your result.
Okay, thank you. Yeah, okay, thank you. Yeah, yeah. So I think that we have plenty discussion. So I think that we should close the seminar. So let's thanks again to Professor Hiyama for very nice talk and very deep discussions. So I conclude that the seminar is closed. So thank you very much. Thank you all.
Thank you very much. Okay, so next time we can see you each other by face to face.
We are looking forward. Okay, so I will.
See you.
Yeah.
Bye bye.
Yeah. See you. Bye bye. Bye bye.